Greetings all, good afternoon. We're bang on time. We'll give people a few minutes to come through the turnstiles, but thank you for everyone who's already dialed in. I hope you guys can hear me okay. Please let me know if you can't. And look, before we dive into the presentation from Craig today, just a bit of Ocean Protect news. So just give people a bit of a chance to come through. But for those who aren't familiar, Ocean Protect actually turned 20 years old just this month. So kudos for everyone who's been there since day one and beyond. So congratulations all. If you're not already a fan of the podcast, and I know Craig is an avid listener, isn't that right, Craig? I think we're well over 130 episodes now on the Ocean Protect podcast. We had it's like having kids. You shouldn't have a favorite, but I reckon our most recent one with Dr. Mitchell Call and James Sippo from Southern Cross University about the flooding in Lismore in late February is an absolute doozy, and I reckon it's my favorite of all time. And if you haven't listened to that already, please do so. That's an absolute cracker. Talks about the rescue and rehab and the links to climate change, etc. And look, obviously you're people that like virtual events if you're dialing in today, but we're bringing back several face-to-face events, us, Ocean Protect, and others. So just a very quick plug for a couple of upcoming events. First up, just in a week or so, is in Brisbane for the Brisbaneites, Stormwater Queensland event, looking at the future of stormwater management in Queensland. So please jump on the Stormwater Queensland website if you can make that one. Also, if you're in Adelaide, and I know we have a international, but certainly a lot of people from interstate. If you're in Adelaide in September, there's also the South Australian Stormwater Symposium hosted by the Civil Contractors Federation of South Australia, and Ocean Protect are a supporter, a sponsor of that. And look, if you can get along, please do so. All proceeds from the day will go to a couple of cracking charities in the Estuary Care Foundation and OzMap as well. So also back in Brisbane and Stormwater Queensland, they've got their Sustainability Summit, their conference for the year, happening in October. So if you're keen to attend, please check out the Stormwater Queensland website for further information. Also, if you're in Cairns, North Queensland, there's another event happening in a week or so in up that neck of the woods. So Australian Marine Science Association, and yours truly will be presenting about that, talking about stormwater. Would you believe? Who would have thunk it? And also, if you're this is all around Australia, but the Sea Shepherd guys are putting on an ocean defence tour. And they've got a stack of events in November around various states and territories in Australia. So jump on the Sea Shepherd Australia website if you're able to or keen and able to attend any of those. And again, Ocean Protect are sponsoring or one of the sponsors supporting the cool cats at Sea Shepherd in their activities there. Just a reminder, for all of these webinars, including today, they are all available on the Ocean Protect website under oceanprotect.com.au/webinars. So that includes all the recordings and all the presentation slides, and obviously provides details on upcoming webinars as well. But look, we're not here to talk about that sort of stuff. We're actually here, we're very privileged. I think for his... Now, he reminded me before, it's his second appearance on an Ocean Protect webinar. He did also make a guest appearance as an esteemed panel on a Stormwater Queensland, Stormwater New South Wales webinar not too long ago. But Craig, for those who aren't familiar with Craig, he's dialing it all the way from Portland, Oregon. Is that right? Not the Swiss Alps today, Craig? Is that right? From
yeah,
Portland
that's
today?
correct. Yeah, I'm faking you guys out with the
background. I can't hear you.
Yeah.
Is that my audio? Might be mine. Just give me a sec, Craig.
Sure.
Is that my audio? Can you sing a few bars, Craig?
I won't sing you some bars.
Oh, I can hear you now.
Can you hear me now?
I think it might have been my end. Sorry, I don't know what.
I have a guarantee for that, Brad.
I was hoping you're going to bust out into a song, Craig. For those who don't know Craig, apart from being an amazing engineer, he's actually a rock star. He's a genuine rock star. But I'm not going to make him blush any more than he has already. But for those who aren't familiar with Craig, he is the regional regulatory manager for Contech Engineered Solutions, covering 12 states in the US. And look, he's wearing many hats, but he's got a BS and MS in environmental engineering from Portland State Uni. He's a member of the American Society of Civil Engineers and the Environmental and Water Resource Institute, ERWI, the Urban Water Resources Research Council, and is also a chair of the EWRI Stormwater Media Filtration Committee. So he's highly engaged in all sorts of activities around the US, and he's certainly, we're very privileged and excited to have him sharing his wealth of knowledge in relation to biofiltration systems today. So without further ado, Craig, I'll pass over the reins to you. And just a reminder, whilst Craig's loading up his presentation, number one, thank you to everyone who's dialed into today's webinar, a very popular webinar topic. And just a reminder, if you do have any questions you'd like to ask Craig, please put them in the Q&A panel. So it's generally a case of first and best dressed. And we do have a lot of people dialing in today. So if you have a question you really like to ask Craig, please do so. But please put those questions in the Q&A panel. So Craig's going to do a presentation. We think maybe about 25 minutes, and then we're going to dive into question and answers with attendees. But again, thanks to everyone who's dialed in, and thank you to Craig for giving up his time and energy to prepare and present today. It's certainly got a lot of interest, and I have noticed there's quite a few international guests dialing in. I noticed the godfather of Stormwater, Jim Lanhart's dialed in today. Greetings, Jim. But over to you, Craig. Thanks again for presenting today, and I'm looking forward to it.
No, thank you very much, Brad. Can you see my screen okay?
Yeah, it looks great, Craig.
Wonderful. Okay, yeah, thanks so much to Brad and the folks at Ocean Protect. Always happy to share whatever knowledge and tidbits I can on stormwater with all you practitioners out there in Australia. Hopefully you find this information useful. The title's a little bit different here on the slide. I've given this presentation a few times, but we're going to be talking about laboratory analysis of stormwater control measure, mass load capacity, and long-term performance. In pure English, looking at stormwater control measures, how long do they last, and what makes them clog? So for the focus of my research, this was a research conducted for a master's at Portland State University. And I looked at two different stormwater control measures. I looked at a conventional bioretention or rain garden system that you see there on the left. That's a local City of Portland, Oregon rain garden there. And then that's kind of a lower flowing device. And then I looked at high rate biofiltration systems, similar to the stuff that Contech and Ocean Protect manufacture. And that's a Filtera system there in the middle, flowing at a much higher rate. And I ran these systems to failure and using different synthetic stormwater to understand, maintenance needs and what makes them clog and need maintenance and what affects that long-term performance. And the picture on the right there, I started this research right when COVID broke out. Fortunately had the foresight that my university would be closed, and it was. And so I got all my gear and set up, put my experimental setup together in my garage, affectionately termed the Garagetory. So that's a little shot of it there on the right. Ran water quality trials in there for about a year and did all the wet lab analysis at the Contech lab in Oregon. So a little bit of background, stormwater is the only major source of surface water pollution that's increasing in the United States. I'm sure it's a similar problem in Australia, hence the presence of folks doing good work like Ocean Protect. A couple acronyms I'll be using, SCM for stormwater control measure, that's what we use in the States. So if you hear me say SCM, that's what I'm talking about. BRT for bioretention, the public domain lower flowing systems, and HRBF for high rate biofiltration, and kind of those higher flowing biofiltration systems. And here in the States, and I think similarly in Australia, often when we're designing these systems, we have numeric reduction targets. The most common one is 80% total suspended solids removal. And how we verify these systems work, whether it's a manufactured system that Ocean Protect or Contech manufacturers, or it's a public domain system, we need some sort of performance verification and assurance that these are going to be meeting our water quality goals and protecting receiving waters. And here in the States, manufactured devices, we really have to go go through some serious testing protocols. We have a field monitoring protocol out of Washington State, and we have a laboratory protocol out of New Jersey. And these are some really robust testing protocols. The Washington State Ecology Field Protocol can cost over $200,000, take up to 2 to 5 years. So seriously rigorous testing protocols, as there should be, to protect our receiving waters and make sure these systems are hitting those benchmarks. And just wanted to note here that public domain devices, these systems are tested a lot differently. They're usually, researched by academia. Sometimes some local jurisdictions will do some monitoring, but there's definitely kind of a gap, at least here in the States, on how public domain systems are verified versus how manufactured devices are verified. And that was kind of a secondary goal here that I wanted to look at in my research was when I was evaluating that public domain bioretention system, I used a manufactured treatment device, rigorous testing protocol in the lab to see how well that would do. And so when we're talking about those numeric benchmarks, it's great if we can remove 80% total suspended solids, but the question, really the billion-dollar question is how long does it remove pollutants and protect receiving waters? And the answer is really about maintenance and how often the system needs maintenance. We know here in the States, unfortunately, a lot of times we see these systems clogging prematurely and not doing their job. There's a picture of a bioretention system there on the right. It's not supposed to have standing water. It's clearly clogged and can't process pollutants and runoff. And so it'll likely need to be replaced. And so kind of, how do we, kind of driving a question here behind my research is, how do we enforce and test systems for maintenance? That's a really difficult thing to do. And so here in the States, the New Jersey Department of Environmental Protection does have a laboratory testing protocol for filtration devices, and they also have a sediment loading protocol. So they do take a look at this stuff in the lab in this protocol in the United States. And what they use though for their test sediment is something similar to what you see there in the bottom left, which is kind of a clean inorganic silica. And this is kind of their surrogate for TSS and testing these systems. And for over a decade, we've known as stormwater practitioners, this is not really representative of real stormwater, which is closer to something there in the bottom right that has all that nasty stuff, organics, motor oil, oils and grease, hydrocarbons. That's the stuff that we think clogs stormwater systems. And we've run Contech and other manufacturers have run our systems through these different protocols in the lab with the synthetic sediment and then in the field with real stormwater, and we notice a big difference. We can push a lot more water through these systems in the lab when they're only using the inorganic silica. It makes sense, it's clean, it's not sticky. And then we notice in the field when we're testing these systems that they can't process water as fast. So there's a big difference there. And so that's kind of what I wanted to test was kind of to show, hey, when we're testing these systems in the lab and we want to understand how well they perform and how long they perform, we need to be using some additives to better represent actual stormwater in the lab. And so the objective of my research was to determine the effects that synthetic stormwater made from silica, organics, and motor oil have on stormwater control measure mass load capacity versus just silica sediment alone. So again, I tested a conventional bioretention system there on the left and a high rate biofiltration system there on the right. I ran both of these systems with just the inorganic clean silica sediment using that New Jersey protocol. And then I ran the exact same test on the exact same system with that clean silica, but then also added motor oil and organics to try and demonstrate that, hey, when these systems are in the field and they're hit with real stormwater, they're probably going to clog and need maintenance a lot faster. So here's another shot of the garageatory. I used, fortunately, there was a high rate biofilter. Filtera had been through the New Jersey protocol in 2014. So I kind of had a baseline to kind of base my setup on and kind of make sure that the garageatory was up to snuff, for lack of better terms, and giving us decent results. And so you can see here, hopefully you can see my pointer. I used a slurry tank here on the right with a couple paddle mixers and a recirculation pump to kind of get a consistent influent concentration. I used a big 275-gallon source water tank to kind of mix it together in the right concentration. I delivered it all through a flow meter that measured flow every 15 seconds. And then the high rate biofiltration media was stored in this 55-gallon drum here. And I tried to use some larger columns here because laboratory testing, a lot of the bench scale stuff with smaller columns, I don't think it really does a great job representing performance of these systems, and especially clogging. And so I wanted to have something as close to full-scale systems as possible to really represent that full surface area and clogging mechanisms that we might see in the field. And so for this high rate biofiltration column, I ran it similar to the Filtera system. I ran it at 140 inches per hour, so a really high rate. I used 4 inches of underdrain stone, 21 inches of engineered media, and 3 inches of mulch. There's just another little shot there of the slurry tank and the source water tank kind of coming together in a manifold. And you can see the top of the high rate biofiltration system there. That's the top 3 inches of mulch. And for the conventional rain garden and bioretention system, again, I used the city of Portland, Oregon out here in the West Coast of the United States. I used their local bioretention mix just because it was really readily available and local and easy to source. But also they use a 60% sand, 40% compost blend for their media. And this is a really common blend that we see in the United States. And so it's gonna be representative of a lot of places in the United States. And the Portland spec was the conventional bioretention spec was at 6 inches per hour, so much lower flow rate. And here's a shot of setting up the conventional bioretention system. Since it flows at 6 inches per hour and it's a lot lower flow, I actually housed the City of Portland bioretention media in this white 275-gallon tank. It needed to be a little bit larger to accommodate that small 6 inches per hour rate. And let's see here. And then there on the bottom left, that is a colleague of mine, Michael Gillette. He is an engineer that's a professional engineer, registered engineer in the state of Oregon. And he's familiar with designing these systems in Portland. And so I had him come out and kind of verify that I was installing the system correctly and to Portland spec. And you can see with a thumbs up, I passed. We got this installed to City of Portland spec. And something interesting to note, remember this slide when we're looking at data in a few minutes here. This is where I sourced the City of Portland bioretention media. They have a blended soil vendor and hauler list that contractors can go to and pick one of these vendors. And these vendors are mixing the Portland bioretention media to specification. And you can see for the first trials, I sourced there in August. It was stored outside in dry conditions. And the second time I went back to source it in December, a little bit different, same supplier, however, a little bit wetter conditions you can see, and it was covered. But just remember this slide when we're looking at data in a few minutes here. A little bit about the protocols that I use to test the system. So the New Jersey filter protocol starts with the removal efficiency trials. You have to run the systems for 10 trials of about a half an hour minimum. You're pulling 5 grab samples, and you have to hit 80% TSS removal efficiency for all 10 of those trials. And that's how you pass their filtration protocol. But then, as I mentioned, I'm really focused on how long these systems last and when they need maintenance. And the New Jersey protocol has a sediment loading trial. So after you finish those removal efficiency trials, you move on to sediment loading trials. You double up the concentration to try and artificially age it, and you run the system until it clogs and fails. And New Jersey defines failure and when the system needs maintenance in their protocol. There's 3 different metrics. And the first one is when it starts to drop below 80% TSS removal efficiency cumulatively throughout the whole trial. The second failure mode is when the system has too much head loss. So when it goes into bypass and it starts to bypass pollutants and runoff. And then the third failure mechanism where you have to stop testing is when the effluent flow rate starts to drop. So if the system starts to clog and can't process 90% of the treatment flow rate, that's when New Jersey says, hey, stop the test, you're done. That is the mass load capacity of the system. And really important when you're testing these systems, New Jersey, any stormwater control measure, the performance is highly dependent on the particle size distribution of your pollutants and your solids coming into it. And as such, New Jersey has a really tight spec on the particle size distribution. There it is in black with your particle diameter on the x-axis and percent finer by mass on the y-axis. And their G50 is about 75 microns. So it has a lot of fine material all the way down to between the 1 and 10 micron range. And my test sediment is in blue there, a little bit finer, G50 of 60 microns. And for the organic trials, when I added that organic stuff that's more representative of stormwater, there's no protocol, there's no real specs for doing this. It's somewhat new. And so I did a literature review to try and figure out how much organics I should use in my synthetic stormwater, and landed on about 30% organic to inorganic ratio. And I wanted to use something that was replicable and that other people could use if they wanted to rerun this test, and that was very simple. So I just used some off-the-shelf compost from a local home improvement store that had, specs already built into it from the U.S. Composting Council. And but something important to note, I didn't realize that the compost is actually only about half organic matter by weight. And so my synthetic stormwater blend only had about 15% organics in it and 85% inorganic. And again, there's no specs for how to process this stuff and run it. So I wet sieved it to get rid of all the large stuff. I let it sit for 24 hours to kind of get rid of all the fine stuff and the clays, and decanted it, rinsed it in the laboratory, made these kind of stormwater brownies that you see there in the bottom. They did not smell like brownies you wanted to eat. But that's the kind of sludge and stuff that we would see in real stormwater. I threw it in the oven for about 1 to 2 days at 100 degrees Celsius, baked off all the water, and was ready to go. But back to those slides on particle size distribution, that stuff really affects how systems work. And so, when I was adding the organics to the inorganic sediment, I wanted to double check particle size distribution and make sure that wasn't just throwing off my whole test. So I ran a bunch of hydrometer sieve tests. And there's that particle size distribution again with the New Jersey spec in green. The inorganic particle size distribution is in black. And then when I added the organics to it, that 15% organic matter, those are the results there, 3 samples in red. I was pretty stoked that everything lined up on the higher end here, matched up. Honestly, I think it was somewhat of a miracle that it matched up on the top end and the bottom end here. A little bit of disagreement in the middle. But what happened when I put that organic sediment in there, it made the sediment a little bit coarser than the New Jersey spec, but I think close enough for this analysis. And for motor oil, I did a literature review, just trying to find out exactly what kind of concentrations to use for motor oil. I landed on about 7 milligrams per liter, and just used off-the-shelf 5W30 here in the States. That's a common motor oil. And on to results here, the good stuff. So what you're seeing here is the results for the inorganic clean sand sediment high rate biofiltration column. And on the x-axis, that is net sediment load in pounds per square foot. So pounds of solids per square foot of media and the high rate biofiltration system. And then removal efficiency of TSS there on the left axis. And again, I used an already existing test that was done through New Jersey as kind of my baseline. It was a 2014 Filtera test, and that's in the orange with the triangles representing the average over time. And then my trials in the Garageatory are in the blue triangles. And so I ran the system for 69 trials, loaded about 63 pounds of that clean inorganic silica into the system, and it failed by 9 inches of ponding and going into bypass. And you can note, I was pretty happy. The removal efficiency is a little bit different. I was off, maybe about 10% from the 2014 Filtera. I think there's a few reasons why this could have happened. Probably because I used a slurry tank for introducing sediment into the system versus an auger. That could be a difference. But in general, I was pretty happy that I saw a similar trend in decline as I was loading this thing up with mass. It kind of failed and clogged in a similar manner, and almost almost nearly on the same amount of sediment load. My column actually went a little bit longer, a little bit lower removal efficiency, but lasted a little bit longer. And here's what happened when we added organics and motor oil to the test sediment. The high rate biofiltration system only lasted 13 trials. Again, it failed by bypass and 9 inches of ponding, and only processed about 5.3 pounds of sediment. And working for a manufacturer, when I first saw this, I thought it was a little bit troubling. But when we plot both of these together, and you can see here clearly, when you have the inorganic sediment, the system lasted almost forever. And then only 13 trials when you add the oil and organics, and this came out to about 1.9 pounds per square foot. But when I went back to look at our field studies and compare this to some high rate biofilters we have in the field, this was actually spot on with what we see in the field with real stormwater. We see anywhere between about 1 and 2 pounds per square foot of loading when we're using real stormwater. So it wasn't that my system failed fast in the Garageatory, it was that it actually mimicked what happens in the field. And this New Jersey test with the clean inorganic silica just really overestimates how long these systems perform. And so I was pretty happy to see that this lined up with field results, but really clear results here. If we're looking to understand how these systems, how long these systems last, and when they need maintenance, we need to be using something in the laboratory that's a little bit more representative of real stormwater and adding some oil and organics in there. There was almost about an order of magnitude difference here in how fast the system will clog when you're using just inorganic silica or adding oil and organics to it. Moving on to the conventional bioretention system, the public domain City of Portland system. This system, I actually couldn't run it to failure. Again, it's operating at a really low loading rate at 6 inches per hour. And so I ran it for 117 trials. I loaded it with 24 pounds, about 1.8 pounds per square foot. And I think what happens in this case with such a low flowing device, it's really just building up that clean inorganic silica and kind of creating a sand filter on top of the bioretention system. And so this thing probably would have lasted forever. I'd probably still be in the garageatory to this day if I was trying to run it to failure and just piling sand in there. And so I called it at 117 trials because I wasn't really interested in how long the system would last with clean or inorganic silica. I just wanted a data point that I could compare when I loaded it with motor oil and organics. And so ran it for 117 trials. Surprise, surprise, when I loaded it with organics and oil, in addition to the clean silica sediment, it only lasted 31 trials. And the bioretention, the public domain system, it didn't fail by bypass and ponding. It actually failed by dropping below 90% of the treatment flow rate. So that graph you're seeing there, it's again net sediment load in pounds per square foot on the x-axis, and that's flow rate in GPM on the y-axis, and the red line, that's that 90% treatment flow rate threshold. I believe the design flow rate for this one was 0.83 GPM. So you can see it kind of struggled a little bit in the beginning, and then towards the end, it started to drop below 90% of the treatment flow rate, and that's when New Jersey would call it quits on this system. So it loaded about 5 pounds into the system. And looking at TSS for this second public domain bioretention system, it really struggled. If you can see here in the beginning, we'll talk about this more in the next couple slides, but the system really struggled to hit 80% removal in the beginning, and it was really due to a media instability issue, and I think a QA/QC, maybe a storage issue. If you remember that slide where this media was sourced at a different time of year, at a different place, same specification, the system was pretty much leaching out its own media. And if this was going through the New Jersey test, through the manufacturer treatment device protocol, New Jersey would have said, see ya, you did not pass the test. Although notably, it did start to leach less and less media, and it did eventually recover and start to get up to 80% TSS removal. But same story here when you compare the inorganic clean test sediment in blue to the inorganic, organic, and oil sediment there in green, nearly an order of magnitude difference. And so, really clear results here that when we add oil and organics to our test sediment, our systems are going to clog a lot faster. And it's probably going to be more representative of what happens in the field. And so another slide on that kind of flushing that I saw with the media attrition that we saw with the conventional bioretention system. It was for all media systems need a little bit of rinsing, a little bit of ripening. And so for all of these systems, I rinsed them with clean water and got them to a turbidity reading of below 20 NTUs before I started the test. So once I hit 20 NTUs, that's when I started the trial. And you can see here in this table, the first two high rate columns, no problem, got below 20 NTUs, reasonable flushing volume per cubic foot of media. But that last bioretention system, I could not get it down below 20 NTUs to get started. There's some pictures of the effluent bottles there. Before I even started testing, it was just clean water. And you can see that the effluent was this dark brown color. Not very pleasing to see. And I couldn't, I flushed it with over 2 times the volume and still couldn't get it below 20 NTUs to get started. But this is a master's thesis I had to get done, so I just got started. But clearly, this was an issue with media QA/QC. I did take some TSS samples. You can see down here in the left, it started off at a nasty 700 milligrams per liter and started to taper down when I got started to about 89 milligrams per liter. But looking at the total mass, estimated mass of how much media this system flushed out before we even started testing, it was about 7 pounds. So not a good thing for this public domain system and the media, this media. And in addition, one thing that we know here in the United States that we've been seeing for the past decade is 40% compost. We're using too much compost and bioretention media. It does leach phosphorus, and this is not a good thing, especially for phosphorus limited receiving waters. This is the effluent from both bioretention mixes, the lower flowing stuff. Effluent, there was no phosphorus that was input into the system. And so this was all coming from the media leaching out, and it was leaching out at a rate of 4 milligrams per liter was approximately the highest. Pretty nasty stuff. It was almost all dissolved, about 84% dissolved phosphorus. We know this is a problem here in the United States. We're trying to get jurisdictions to kind of change their specs. Some are kind of on the forefront and changing with some more robust specs, but to get a really good engineered media, it takes a lot of QA/QC, a lot of testing. It really is an engineered media. It's not just a simple spec that someone can throw together. And so I'll stay on the soapbox for just another minute here. Why this happens in the United States, there's really a focus on healthy plants, means that you're getting good water quality. And as you can see in this picture, it might be great for the plants, but it is not great for effluent quality. And I kind of rib a little bit that, this isn't here in the States, it's the Clean Water Act. This isn't the Landscaping Act. This isn't the Pollinator Habitat Act. We're looking for clean effluent water here. And so, really, we need to have an engineered media that's all about your media if you want to hit your water quality goals. And that is some shameless self-promotion. As Brad mentioned, I am chair of the EWRI Stormwater Media Filtration Committee. And this is part of the American Society of Civil Engineers here in the States. And we're putting together a technical report on filtration media. And so we welcome international participants. So if there are any other stormwater nerds out there that are really interested in media and treatment, my contact is on the end of this presentation. Feel free to reach out to me and I will get you plugged in if you would like to participate. But some quick conclusions, run a little bit long here, I apologize for that. The mass capacity of these systems is definitely lower when we add organics and oil to silica test sediment. And when we're testing these systems in a lab, we really should be using some oil and organics to get representative performance and kind of match what's happening in the field. Other big takeaway, that bioretention media stability, the public domain stuff, it can be very variable in performance. And in this case, it demonstrated some significant leaching of solids and nutrients. This is something that we see in the States that's pretty common. And to resolve it, some better media QA/QC can definitely improve your removal efficiency results. And some quick next steps out here in the States. I'm hoping to get involved with ASTM and get some standard methods for using oil and organics in your test sediments so that we can have some protocols to be able to test the performance of these systems, and most importantly, the long-term performance and maintenance and mass capacity, so that, hopefully when we're designing the systems in the future, we could test them and make sure that they're lasting a long time and protecting our receiving waters. All right, I think that's all I have for today. Big shout out to my lab cats. Alice on the left, BMO on the right. There's another glamour shot of the garageatory. If you're having trouble sleeping and you need to read my 130-page thesis, there's the full open access link there at the bottom. You can download it. There's my contact at the top. Brad, I think we can take some questions now.
Yeah, cool. Wow, that was fascinating, Craig. Yeah, there's a lot to take in there, but and just a reminder, folks, if you do have questions, please put them in the Q&A. Please don't put your questions in the chat. It'd be greatly appreciated if you put any questions you might have in the Q&A panel. Yeah, look, I'm going to start off with a question from Ross Cumming. Ross asks, RENY 90% rule for failure. That's the, I think it means New Jersey protocol rule of failure. Would you therefore design the system for, say, 5 times the actual loading than a pass rate of 45%, or something much less than 90% on the over-designed system would equate to 90% on the actual flow rate?
I see what Ross is saying. I think Ross is saying, if you have a system that's failing a little bit too early, would we then want to go and over design these systems to be able to last a little bit longer and kind of build in a safety factor? I think that's one way that you could go about it. However, as I'm sure people in Australia know, when you have these lower flowing bioretention and rain garden systems that are flowing at 6 inches per hour, they're really large. That's why I think folks like Contech and Ocean Protect got into this space, is to provide a smaller solution that can treat more water in a smaller space, especially in these urban sites. So I'd say go for it. If you can design your bioretention system to be 2 or 3 times larger and you have the space for it, that would be one way to solve this problem. But, however, if you're using that same mix, then you're jacking up the cost, you're jacking up the, excavation installation costs. I think, and these systems already have safety factors built into them. So I would suggest, go the other way and work better on an engineered media, and work on your media spec would probably be a better choice.
And just on that, so what would you, and sorry, just a couple of things. So in terms of size, how big are conventional bioretention systems in the States relative to the upstream catchment? I've heard is it sometimes often 5% of the upstream catchment? Is that correct?
So it really depends. So some arid regions will be 2%, but some regions are up to 10%. We've seen, that have a larger rainfall, like Minnesota, I believe, is a jurisdiction I work in. They get about 32 inches annually, and their design storm is about 1.1 inches. And yeah, they recommend between 5 and 10%.
So to put that in perspective, Craig, in Australia, like in Queensland, we have in Brisbane 1.2 meters per year. Our systems are generally 1.2% of the upstream catchment. So our systems are generally actually quite smaller. So that risk of failure, whether it be clogging or whatever, or decreased performance, is probably much higher than the state systems because they are so much smaller.
Absolutely. I think I would agree with that. The 2% example I gave is from Denver, Colorado, and Colorado systems, and they only get about 15 inches of annual rainfall. So that's why I think they have a lot smaller of a system. But in general, though, I hate to knock on this, but I think we can do a lot better than just throwing 8% target, of the upstream catchment, when we're sizing these systems. Personally, I mean, here in the States, I haven't seen a ton of data, at least robust technical field monitoring data on longevity that really shows that those blends can kind of last that long with that ratio. And that's where I think, the testing protocols that I used here and that manufacturer treatment devices use, I think, as we start to use those for public domain devices, we can get a little bit more refined than just throwing out a rough, percent of a catchment area. And I didn't mention that, but we are working on that here in the States. There is a nationwide testing protocol that we're working on that will measure performance of proprietary devices, but also the public domain stuff.
And you mentioned that EWRI group developing an appropriate filter media specification. That's currently just a US-based initiative. Like, are you getting much international, dare I say, Australian input or feedback?
We'd like to. I know that there's definitely some folks out there that are interested. And to be clear, we're putting together a technical report on stormwater media filtration. So we're covering, types of media, properties of media, their application, sizing, design, maintenance. Because what we see here in the States is kind of this fractured and siloed research going on all across the country, and we all have these great lessons learned, and kind of putting it all together into one report that kind of synthesizes all the latest and greatest. So yeah, I mean, we haven't got a ton of international participation yet, but we definitely welcome folks internationally to participate.
And just on the topic of, I guess the fundamental question is, you're seeing results that are indicating that bioretention systems are leaking solids, phosphorus, for example, not achieving what they're actually designed to be put into the ground to achieve. So the fundamental question is, does conventional bioretention systems work? Like, I've asked this question many times. I presented on it. I present the data. But in your opinion, are these systems achieving their design intent?
I think that's kind of a range all across the board. We have over 20 years of research from a ton of wonderful academia, universities across the country, that have demonstrated these systems work. But I think it comes down to what the testing protocols are and how they're testing them. I think that, there are a lot of great researchers that have come across some really good blends that have been demonstrated to work. But I mean, these are academia studies putting these things together. I think your question is valid in real life. When contractors are putting these systems together, no knock to contractors, but they're engineered systems. A lot can go wrong between, when an engineer provides a spec, it's meeting a city spec, and the contractor puts it in the ground. There's a lot of modes for failure there. As we saw, I grabbed just a batch, at the wrong time of year, and it bled out a ton of media. So I think the systems can work. There is a really good kind of aggressive and progressive spec out of Washington to to kind of address this phosphorus issue. It has coconut coir blended with the bioretention media. It has compost on the very top, and then it has it has some active ingredients and a sand layer in the bottom. So it's this really sophisticated kind of multi-layered approach that they're getting better results to kind of fix that phosphorus problem. And dare I say, they're trying to kind of replicate and catch up to manufactured systems where, things like Filtera have been around for 20 years, and we have the R&D, 20 years of R&D into this stuff. So we've kind of figured out a lot of these problems along the way. But so I think they can work, but I think it just takes a lot of QA, QC, and a lot of research to get it done.
And you're talking about specifically the media, aren't you? So like we almost all the discussion has been about the media. There's been no sort of discussions around the importance of vegetation, for example, or whatever. Are you finding that the variability in terms of performance and I guess the fundamental aspect of it, ensuring that a system will work is the filter media specification?
Absolutely. I know the focus here in the States is always on the plants, and people always are focusing on, like I showed in my slide, healthy plants equals water quality. Plants are important. They do provide a ton of, pollutant remediation, or some, I should say. But from my perspective, being a media guy, I feel like the vegetation, while it does provide some pollutant removal benefits, I think the vegetation is really about longevity. I didn't test with vegetation in these systems. That's something I would like to do as a next step. But I think the vegetation is really critical for kind of regenerating the hydraulic capacity of these systems and kind of, opening up the pores and closing it as the roots kind of expand, decay, and die. I think that's kind of the most important feature of plants. So another way to say that, there are some manufacturers out here that manufacture these systems that will install these systems without a plant. And so it's really just a sophisticated engineered media at that point, and they're still getting good water quality results. But again, I think that the vegetation component, while it helps with removal, I think it really is just critical to longevity. And so for water quality, it's all about that media, and the particle size distribution spec, the materials you're using, the different active components. If you're using active components, the target dissolved constituents, it's a really fine recipe to get it right.
Cool. I've got some more questions, but I've had one pop up from Benjamin Peneleric. Greetings, Ben. He's from Water by Design under Healthy Land and Water, and formerly of Blacktown City Council. And Ben says, in developing a new specifications for Blacktown City Council in West Sydney, we saw large variability in test results from what was considered homogeneous mixes. This was put down to the sensitivity of the testing methods. For commercial testing, what do you see this in the States?
I would say I don't personally have a ton of experience working with the public domain media, but on our filtration committee, we're starting to see actual media suppliers that specialize just in stormwater media. And, working with those folks, they do see if you don't use the test methods, I guess I should say it's a two-part answer. The test methods for sure can skew your results and kind of give you false positives on what you think is happening with your media. So having the correct analytical methods, which is something my counterpart Mindy, who's presented for Ocean Protect, is much more well-versed in than I am. But analytical methods definitely play a big factor. But then he hit on another good point. When you're producing just tons and tons of this material, what is a representative sample? How homogeneous really is it? How often do we need to be testing it? I know that folks like Ocean Protect and Contech, we have our own internal QA/QC procedures where we check every batch for X amount of parameters. I think that varies widely for public domain systems. At least here in the States, if it's even done at all. I hate to say it, but there's some states I work with that they will literally just dig a hole in the ground, grab some native soil on site, throw it in, put it under drain, and put some plants in and call it good. They think it's like a gardening feature or something. They don't realize that this is, an engineered system to meet a clean water permit.
And just on that issue of the differences between what you call public domain systems, so I'm guessing like conventional bioretention systems, wetlands, etc., and compare the testing requirements for manufactured devices. You're saying like manufactured devices in the States have to be appropriately tested to a very, very high standard, etc. But historically, there's been very little testing requirements for these public domain systems. We see that in Australia, but I'm just keen to get your perspective as to why is that the case in the States? Why is there almost this blind faith, or at least less informed faith that these public domain systems work, and there's such a high level of scrutiny on manufactured devices?
I think it started off, obviously we are manufacturing and selling these systems, and so rightfully so, we should be held to a high standard to make sure that they work. But I think, when stormwater first got started and it was kind of a fledgling field, obviously it was academia that kind of took on the reins of researching this stuff, and academia and universities do great work. But I would just say that as the science evolved and we started to learn more about these systems and learn more about stormwater in general and how variable it is and how difficult it is to test this versus wastewater. Wastewater is a lot simpler. You know almost exactly what's coming in. It's all automated. It's all active. You're testing it in real time, where stormwater is a lot trickier. So I think we've learned a lot of lessons over time, and a lot of these lessons have been put into the manufactured device protocols. I don't know. It's a great question, Brad. I wish I had an answer as to why there's so much blind faith in public domain bioretention systems. And I think this is something we're working hard on with the EWRI Media Filtration Committee to kind of gather all the experts, get everybody on board, and let them know like, hey, this isn't just a simple thing, that we can just trust. 6 weeks of research on. We need long-term data. We need to test specific protocols under X amount of parameters. Using X amount of equipment, analytical methods. The protocol for ecology, I think, is like 70 pages long. It's really robust. And so, I don't know why we're still in that boat with public domain devices, but as I said, there is some momentum here in the States to kind of get public domain systems tested. And just one last quick thing I'll say about it. As a youngish environmental engineer, I've been in the field for about, not young in age, but young in study. I've only got about 8 years under my belt. I was actually pretty shocked to learn that, my fridge, for example, has a sticker on it and it's tested under a protocol to tell me I'm saving $5 a year on energy. But to protect our rivers, oceans, and lakes, we don't have testing protocols, and there's just kind of not adequate sometimes conventional systems put in the ground. That was honestly shocking to me. I still don't know to this day why we have all these protocols for all these other devices and all these other things, but we are not doing that for clean water.
Yeah, look, similarly, I was shocked, and I speak from experience, I've been doing this for about 18 years, but, modeling bioretention systems and wetlands and whatever in music, our software program over here, there's this assumption that it's an appropriate method of predicting performance. And when I sort of delved into the science more, I just couldn't believe. And I was like, how come no one else is asking these questions that I'm sort of putting forward? And I present the data, I present the studies that I can find on conventional systems and basically show the points that you're sort of talking about, the high variability in terms of performance at the very least, and often high rates of nutrient leaching from conventional biosystems, et cetera. And no one seems to be paying any attention. Whereas if we've got any device, and I rightfully acknowledge, I think it's appropriate. If we've got proprietary devices, they have to be appropriately tested, peer-reviewed, published journals, et cetera, which I think is fine. But just that there should be that requirement to demonstrate these public domain systems, because often they're providing a bigger role, given they're generally more widespread than our proprietary devices. It's bizarre. Ben, sorry, you go. Sorry.
Oh no, I was going to say thanks. I was going to address Ben's comment here. Appreciate the kudos there. And I think just kind of ripping off what you said, Brad. I think at least here in the States, stormwater is kind of the last thought when you're thinking about funding. When civil engineers are designing a site, stormwater is kind of the last thing. When their cities are thinking about funding, stormwater is kind of on the bottom of the list. And I think it's kind of honestly been a resource issue. I work with a lot of cities and municipalities, and they don't have the chops or the resources or the technical background to really get into the weeds and understand this stuff. And that's where I think we really need guidance from like a regulatory standpoint or from a national organization standpoint to give people the tools to be able to evaluate how well these systems are working. Also, I think there was no kind of there was no one around to kind of poke holes in kind of the academic research, and how these systems are working in the field. There was no impetus for that, but except for when, you have Mr. and Mrs. Manufacturer coming along and we're designing these systems to a high standard because we want them to work well and protect receiving waters. And then we look at, what we're quote unquote competing with, or, what the other tools are in the toolkit. And we're trying to hold those up to the same standards and seeing that it's not the case. So I think we have a little bit of an uphill battle ahead of us, but I'm up for the challenge.
Yeah, me too. Me too. And look, people wouldn't have seen Ben's comment, but Ben says, just to follow on from what Craig was saying, he says, not a question, just well said, Craig. You're absolutely right. It's the same in Oz. No monitoring to provide evidence that these things are actually doing what they're meant to. Music is not evidence. Again, just a reminder, if you have any questions that they'd like to ask Craig, please put them in the Q&A. I had a question on the mulch. So you obviously put Filtration bioretention systems obviously apply a small layer of double shredded hardwood mulch on the surface to, minimize clogging and promote longevity. Is that something that's required, or is that something you used in your test for your conventional bioretention system as well?
That is a fantastic question. Yes, I did use mulch in the conventional bioretention system. Is it part of the city spec? No. And so a lot of, there are some jurisdictions across the country that will use mulch, but there's a lot that don't. And, since I am a manufacturer that was running this test on a public domain system, I really wanted to give it, all the chances it could to work really well. So no one can say I stacked the deck. So I did use mulch on the Portland system, the public domain system, conventional system, as you would say. 3 inches of mulch, similar spec. I think they have a mulch spec in their landscaping and part of their manual. So it's a little bit different than double shredded hardwood, but pretty similar. It didn't float. And I think it did a great job kind of acting as pre-treatment, as we use for things like Filtera and high rate biofilters. But that's a great question. I think we would have seen very different results if that mulch was not there. I think the conventional system would have just clogged really, really quickly. Just from observation, I mean, the gigantic pile of sediment caught in that mulch.
Look, I don't want to give you more work to do, Craig, but I reckon that's the next part of your study. If you want to do a PhD on this, I think, because the conventional approach in Australia is we don't generally use mulch on the surface of our public domain or conventional bioretention systems, and I see that as one key learning that we could take from the States, or at least Filtera bioretention systems, is we know mulch provides sort of 2 key benefits: retains moisture, but acts like a great pre-treatment, and we just don't see that applied in conventional systems. I think if you're an owner of a biosystem and you're trying to minimize this risk of clogging, please put some mulch down, and some appropriate mulch. So we use double shredded hardwood mulch on Filtera systems, which is low in nutrients, low floatability, etc. So I'd really suggest doing that. Would you disagree, Craig?
Oh, I absolutely agree. With all the city and state agencies and practitioners I work with, that's one of the first things they ask me about is, what about the mulch? And 1,000% always recommend the mulch as a pre-treatment. Something I want to add is it's great at getting sediment and then retaining moisture for the vegetation. But there's actually some studies in the States that show it's great at removing oil. So, looking at oil being something that clogs these systems, a lot faster, that mulch can actually do a good job sorbing some of that oil and keeping it out of the media and keeping it going.
Look, there might be a good time to wrap it up. This has been, I've thoroughly enjoyed this presentation. There's so much to take in. I think I'm going to have to watch it on YouTube later on. But on behalf of everyone who's dialed in today, Craig, thank you so much for giving up your time and energy to share your knowledge and expertise. It's been really fascinating. It's so good to sort of tap into the experiences of yourself, but obviously the wider US engineering industry. And I'd certainly encourage people, if you want to find out more or have a chat to Craig, please reach out. If you're keen to read his 130-page document, please do so. It's a hell of a read. But also, if you're developing media specifications or keen on getting involved, maybe reach out to Craig to participate in this EWRI group. I know I have. I've just got to start going along to their meetings. They're sometimes in ungodly hours, so sometimes I do miss them, Craig. Apologies, but
I do need to keep in mind when I'm setting those meetings. I need to keep in mind international folks. I'll work on that.
Yes, okay, cool. But thanks everyone for dialing in today. Really appreciate it. There's comments coming through. Awesome work, Craig. Come to Australia and fix our problems, will you? A lot of thanks coming through. So again, thank you for Craig giving up his time. Thanks everyone for dialing in, and enjoy the rest of your day.
Thanks everyone. Bye-bye.